Recording.
Yes, we're recording now. So as we're now broadcasting, I can see the number of participants coming in. So welcome to those early birds for week 12 of our series of TMS Tuesday webinars. You can hopefully see the panel there, and we're just having a chat about the unfortunate events down in Kerala in India last week. Or a couple of days ago, in fact, last weekend. We'll be talking about that in Keith's presentation because visual aids, as ever, in low visibility conditions play a very important role. So, yeah, you've been studying the reports, Paul. I guess
yes,
it's very early days.
It's like any air crash. Until the facts become known, there's all sorts of speculation about what the possible causes are. But one of the known facts is that it was bad weather when the pilot was attempting to land, and for whatever reason, he seems to have overshot the runway. And unfortunately, because of the topography of the particular airport, it's what they call a tabletop airport, which means that the actual airport itself sits higher than the surrounding terrain. So unfortunately, when the aircraft exited the runway, it just went straight down a bank, and that's probably what caused the fatalities and the injuries, because there was no apparently I don't believe there was any particular fire that broke out after the crash. It just crashed, went down the embankment, and then broke into pieces.
That begs the question, of course, that that would, by its nature, if the approach in one direct, well, if you have these drop-offs, that's non-compliant in itself. How do those airports get to certification in those circumstances where the terrain is not flat at either end of a runway? Tony.
Well, there are a lot of airports where the terrain in the approach is not flat. I mean, we're perhaps in the UK, most of our airports are in very flat terrain, but many places in the world that isn't so. No, it could be well, down in the Med, there's quite a lot of airports where it's on the beach effectively, so you've got the sea on one side and maybe approaching. There's all sorts of things, and I think one of the things that was reported was that this was at night, and the piloting comments were the visual cues are very sparse apart from what is actually on the airport. And from what was on the airport charts, not an awful lot, a very short amount of approach lighting, runway edge lighting, no centre line. Yes, a PAPI, it doesn't say whether it was serviceable or not. And a runway, a wet runway with a tailwind landing would have produced, first of all, the tendency to land long, because of the tailwind, and then a wet runway stopping distance, landing distance available may have been inadequate in those wet conditions.
Yes, yes. So we've got, as I say, some more discussion on this particular topic as we go through the actual presentation itself.
Just one thing, Robert, just to say one thing occurs to me about the report. It was reported 2 miles visibility and rain.
Right.
What was the cloud base? Because if it's rain, it's coming out of clouds. If the cloud base was only about 300 feet, this guy may be popping out of cloud not very far from the airport before he sees anything.
Yes, well, I guess all of that will become clear in the course of the investigation, but yeah, it's very tragic for all of those involved, and obviously we send our sympathies to everybody that has been affected in any way on such a terrible occasion. But it is certainly, in our experience and an analysis of fatal accidents, low visibility is a factor in more than 90% of fatal accidents on final approach and landing, which, as we know, is the most dangerous part of any flight. So just reinforces the importance of airfield ground lighting and it functioning according to the standards. So we've got just under 2 minutes to go before we officially start today's webinar. There's been a lot of, as I said, we haven't got a COVID update for you this week, but obviously it's continuing to play having a major impact on affecting our operations, and certainly, you know, from my part, I've been contacted by a number of people who've been affected personally by this, because one of the unfortunate consequences of this terrible disease is that airports are suffering economically, and that has an effect on people's jobs. So I know there's some very experienced people around that are currently available for hire. So so if there are any airports out there, do let me know, and I'll try and do what I can for our friends in the airfield lighting world, because this is you know, there are going to be a number of consequences for quite a long period to come from this terrible disease. Right, well, we're getting 2 o'clock now. It's 2:01 in fact. If I could now officially start today's webinar, very proud to announce webinar 12 in our series of airfield ground lighting webinars. None of us could have imagined when we started doing these webinars, we thought we might be doing 3 or 4, but we've had such positive feedback that we thought that it would be a good idea to continue them. And there's no shortage of subject matter, as we will come to at the end when we announce next week's webinar. I'm very proud that during the course of these webinars, we've had a fantastic team of experts joining us and supporting our activities and our webinars. Of course, led by Keith Costall, known to most of you as you know, airfield lighting guru and trainer and all-round expert on the subject matter. But also we didn't know we were going to be so fortunate when we started that Tony Smith would be joining us. Tony Smith, as you know, inventor of the PAPI, and again, and very much an instigator of the standards, someone who understands why the standards are what they are. So if anybody doesn't understand why the standards are what they are, please ask a question, and we'll address them in our Q&A session at the end of this presentation today. And of course, Paul Smith, who many of you will know from principally from photometric testing world and MARMS. So thank you very much. Paul has a lot of practical experience of hands-on AGL troubleshooting, photometric testing, and supporting airports generally around the world. But first off today, I'd like to kick off with this AGL webinar with Keith Costall, who I'll now hand over to. And so if we dumb our screens down, gentlemen, I'll hand over to Keith. So thank you very much for joining us, and over to you, Keith.
Yes, good afternoon. Can you hear me?
Yep.
Okay. Well, good afternoon, everyone. And I'd like to say welcome. And what I'll do is have to bring my screen up. And at this moment in time, my screen will not move forward. So I will take my screen backwards and bring it up again. Okay. So you just bear with me a moment. For some reason, I've got a lockdown from. Here we are. Now we're. I think we're moving. So let's discuss the lighting function. The lighting function that remembering that every flight, we hope, will start and end at an aerodrome, and the airfield ground lighting. And we've had some questions about what does AGL actually mean. Actually, ICAO referred to it as aeronautical ground lighting, but that aeronautical ground lighting is a wider subject which covers everything rather than just the light itself. So that's why we tend to, when we're talking about the light output itself, we talk about airfield ground lighting rather than the wider subject of aeronautical ground lighting. And it's designed there to support safe and aircraft operations and give an essential illuminated visual guidance to pilots And of course, not forgetting the people who use the aerodrome and the movement area. And it's particularly important when visibility is reduced. So what happens if we do not achieve the photometric output, which is defined for us? So what we're going to do this week is to actually look at the cycle, the life cycle of AGL. I mean, it starts really with somebody's idea. We need a runway, we need a taxiway, etc., etc. So the definition comes up, and then it will go through the design phases. And we've already done some design methodology webinars, and then moving onwards to the manufacturers who produce the product, and that product then has to be installed and commissioned to a standard, and then the airport as an operator then has final ownership, and then it's now into the operational phase. Now, clearly, it has to be maintained and maintained to a standard. So that's the area that we're actually going to concentrate on: the operation, the maintenance, and what we have to produce in the various services to achieve operational compliance. So that's where we're actually going to concentrate this week's webinar on. So when we look at this operate, maintain, and the service side, we need to still understand the regulatory requirements to achieving compliant AGL. And what are the basic reasons for failure? Now, there are a host of reasons why a light does not achieve its photometric output. And we'll briefly touch on it on the various points, the bullet points, but then we'll go onwards to concentrate on what probably the main reason is that we normally experience on an airfield, and how we identify that, and what actions we take to ensure that we can return those light fixtures back as near as practicable to the standard. So and we've got one or two little case studies associated with that. So we'll look at the tools and how we manage the asset. So looking at that picture, if I go back one to that picture on the right-hand side, let's have a look at that picture again. Look at it on the left-hand side as you look at the screen now. What a wonderful picture. But unfortunately, you know, that's a beautiful, like, sun coming up over the horizon, etc. Lovely, lovely shot of an airfield and the approach area. But when a pilot's in the aircraft, the pilot is doing various things. And he's looking at instrumentation, he's looking out the window, the sun is shining, then a cloud comes over the sun, and things change. So actually, there is quite often when a pilot will look out of an aircraft, and then the human being in the eye of the human being and back into our brain is that, oh, that doesn't look quite as bright. What's happening there? And then then this kind of thing happens. So there is a deterioration in the atmosphere associated with the visibility conditions of the day, and especially when those of us that live in an area where close to the equator, for example, how immediately, one moment it's light, and then suddenly, you blink of an eye nearly and it's dark. And although you live up in the north, and it takes an eternity to go dark. And those kind of scenarios, and those kind of things happen in reality during approach. And when it happens during an approach and landing, it can be very disconcerting to pilots. But what about the light fixtures themselves, the light systems themselves? What if that deteriorates? That's something that we can do something about. So that's what we're going to concentrate on, the light fixture inner system. And sadly, we have to report, and we've been speaking about it just before the seminar, sadly on Friday night last in the coastal area in the south of India, in the Kerala area, Calicut Airport, which is on the top of a mountain. It's a tabletop type of a scenario. Then, unfortunately, there was a crash, and it was an aircraft coming in, had been flown in from Dubai, near India, and attempted to land, had to go round, and then there was another attempt to land, and the pilot was able to touch down on the runway, and unfortunately, then because of the conditions, it was in rainy conditions, etc., etc., and unfortunately couldn't stop, overshot the runway, and there was some fatalities. So, as we said earlier, you know, our thoughts go out to all the families and all those people affected by such a tragic accident. But what was interesting that comes out of this is a lot of questions get raised when this kind of thing happens and these accidents happen, and there will be an investigation, but there's lots and lots of speculation. Until the investigation is complete and the report comes out, we will not know the actual cause. And perhaps we'll never know, because sadly, it is reported the pilots were died. So when we're looking at such an incident, and we look at the runway, and then we start to say to ourselves, well, were the lights okay? Well, we don't know that. But there was a report, actually, in 2019, on the 11th of July 2019, was a report from the Indian Civil Aviation Authority Department that there were factors associated with that particular runway. And then a list of actions were defined that had to be undertaken. And one was excessive rubber on the runway. Now, this happens on all runways. You know, this runway is no different. But when you get excessive rubber on a runway in wet conditions, then you get skids, you know, and there are various factors, you know, grooving of the runway. Some airports will put a surface, a low friction surface on the runway, etc. But this happens, and if you get water stagnation on the runway, together with rubber, we're gonna skid. And also in that report, it was identified that there was surface cracking, both are in and around the centre line and the touchdown zone. And there also has been a lot of media reports and speculation, then there's been reports from pilots of that the runway lighting was potentially not up to standard. But we will not know that. But the report and the investigation will identify such a thing. But because runway lighting has been mentioned, then it does lead us to start to say, you know, is our airport okay? And all of you who are watching and are on this webinar today, who are actually working at an airport, I'll point my finger right at my camera and say, is your airport AGL compliant? And can you demonstrate that it's compliant? Because we don't know, and there are lots and lots of airports. Now, thankfully within our group, in the TMS group, then we also have tools which can actually do photometric measurements. We've also got lots of other supporting tools. But when we do photometric measurement, then we can actually demonstrate whether or not the lights on the runway are compliant. Now, in Kerala and Calicut, then the AGL, particularly, there's a shortened approach called the SALS, and the PAPI, and their runway edge lights, threshold lights, and runway end. So basically, it's a precision runway, but operating in the category 1 concept. So it's not category 2 and not category 3. So there's no centre line, no touchdown zone, and no additional lights in the approach. So maybe that's a factor in the future to look at. We don't know. We'll wait and see. So it's really quite appropriate for us to mention this, because runway lighting was mentioned, and it's been mentioned in the press speculation at the time. We have to ask ourselves, so we'll have to look backwards at ourselves and then say, on our airport, can we demonstrate compliance, and how effective and how efficient is our AGL? So we have to look and say, well, what are the factors which ensure that we can achieve compliance? What are the factors which stop us achieving compliance? And we're going to have a look at that and a discussion about those issues. But we're going to concentrate on the actual photometric output of the lights, not on the electrical side or the civil side. So we'll move on from here. So why is it important? Well, it's for pilots, and pilots are the actual end customer for us. Now remember, a pilot of an aircraft approaching and landing on a runway is looking at those lights from distance and height. He's not stood, the pilot's not stood on the runway like we are, looking down and saying, oh, look at our lights, aren't they nice and bright? Oh yeah, go up there at 3 degrees, which is the international glide slope, in lower visibility conditions, and are they still nice and bright? Are they compliant? We have to ask that question. The operator themselves, the airport itself, has a legal responsibility to provide a compliant facility. And the airlines, who are the actual airport's customers, their pilots need to be totally sure that the facility that is offered to them by that airport is fully compliant. And we are one of the facilities. And therefore, when we're looking at the regulatory side and the regulatory standards associated with AGL, then we get inspected. So the local civil aviation authority, which is the representative of ICAO in all our different countries, then they will do an investigation, they'll do an inspection, and they will issue a license. Or will revoke a license if they find that the systems are non-compliant, or give us time to rectify. So let's move on to look at the basic sources of underperforming airfield ground lighting. Electrical. I'm not going to spend time on electrical, so there's a whole range of electrical issues associated with why a light fixture does not meet the photometric compliance. However, what we do in the photometric side, we make sure that the light fixture in a standard AGL system, the traditional AGL system, with the 6.6 amp standard system, then we make sure that there's 6.6 amps being delivered to the light fixture. Without the 6.6 amps, we can't measure against the standard. So there's one fundamental electrical issue, but there's lots of reasons why. There's also internal issues associated with the electrical side, especially now we've migrated from tungsten halogen, which had its own issues, into LED. LED is a DC component, yet we're plugging it into an AC electrical supply system. So we've got to have electronics inside. So there's some issues. Also, some of the components we add, such as ILCMS, the individual light control and monitoring for surface movement guidance, the follow the green technologies. There's incompatibilities there in the electrical side. And so there's a whole wide range of electrical issues. We're going to concentrate on the optical side, but in the optical, we're going to look at internal issues and external issues in the light fixture. That's what we're going to discuss today. There are mechanical aspects associated with light failure, loose securing bolts, say on inset lights, and vibration occurs and the light fixture fails. That was more pronounced with tungsten halogen because it was an element in a gas, so if it was shaking, vibration was a major issue. Obviously, physical damage is something which is to be considered in the different areas of the world, whether, the top of the light fixture being taken away because of snowplow as one such aspect. Or on the civil side, incorrect installation, beam misalignment, etc., etc. Let's go back to the optical side. LED technology replacing tungsten halogens has brought its own demands. And this idea of, put an LED out in the field and your little baby will be at university by the time we have to do something with it. Wrong. It's as simple as that. So with the power supply, with the changing of the tungsten halogen, thyristor-based CCRs, constant current regulators, into IGBT and high-frequency CCRs have brought different interface issues. And I mentioned earlier the ILCMS, follow the green surface movement guidance technology requirements, and then the introduction of the smart light fixtures in the LED technology using PWM, pulse width modulation technology. Again, bringing issues. But let's go back to that optical side. And in the optical side, then we're pretty clear on what we have to achieve, because there's the ISO candela diagram in Annex 14. Edition 8, Volume 1, Edition 8 is the current volume. Every single system, every single light in a system has its own ISO candela diagram. And I've shown two here, two diagrams. One on the center of the screen with that circular looking ellipses are runway related lights. The one on the right hand side of the screen look like rectangular are taxiway related lights. And on the left hand side, we talk about the different aspects of what we check for in the photometric side, the photometrical side of the light fixture. And very, very interesting here. And what I'm going to do here is bring the panel back in, eh? And maybe you guys in the panel will click on your videos again and join me on this one, because very interestingly, do we have a comment on the ISO candela diagram? Certainly from Paul, from your perspective on being experienced of using a photometric tool on many, many airports, many runways around the world. And what is your take on the 5 points that I've made on the left-hand side and the ISO candela diagram itself?
Well, one of the first things I'll point out is that when we measure with the photometric equipment that we have, we are measuring the inner beam ellipse, which on that diagram there you can see ranges from 0 degrees up to 9 degrees vertically, and plus or minus, I think it's 6 degrees, yes, horizontally. And within that beam area, there is the minimum average which you must achieve, but bear in mind that those other ellipses also have a specification, and they're there to assist the pilot when he's not actually staring directly into the beam of the light. But it's reasonably fair to assume that if you're not meeting the standard in the main part of your ellipse, you're highly unlikely to meet the standard in the outer fringes of those elliptical regions as well. Another important point to note is that the measurement grid defined by ICAO is a 1 degree grid. So when you look at our ISO Candela diagrams, the reason they look so blocky in terms of the color picture is because we show you just those measurement points. We don't show you the measurement points, and there we go, we put the keys to move that across to the next slide. We don't show you the measurement points in between because ICAO doesn't specify that that's where we should measure those points. And as we've moved on to the next screen, this is an analysis that I did using one of our photometric workbenches a few years back now. If you look at the grid pattern that has been provided, I noticed on the previous slide, the center line was for a 15-meter spacing. It says there at the bottom, runway center line 15-meter. That goes from 0 to 9 degrees vertically. This particular diagram was for a 30-meter spacing, which goes from 0 to 7 degrees in the vertical plane. So the same principle applies, but I should just use this diagram because this is one that I prepared for another presentation a few years ago. In that measurement ellipse that's been defined by ICAO, there are 52 points at which we make the photometric measurement. So there's 52 points which contribute to that average ISO Candela figure. One of the issues which we see on a regular basis is when the particular fitting, if it's an inset fitting, has sunk into the ground or there's something being put in front of it, for instance, a mastic sealant to seal a crack, or even on a threshold, for instance, grass growing in front of the fixture. And that actually then cuts off the bottom 1 or 2 degrees of the ISO Candela picture. So if we look at the very bottom of that, the point at ground level, there is just one of the 52 points. That's almost 2% of your light output just from one point. If we then go up just 1 degree, we've got another 7 points. So we've now got 8 points to do that 1 degree, which is 8/52ths or 8/52, which is 15.3% of the light lost just if you have the bottom 1 degree of your beam missing or obstructed by something. If we then look at the next row up, that is another 9 points. So we've now got 17/52. So we've almost lost a third of our light average just because we've covered the bottom parts of the beam. Now we'll see in some further slides an example of a light which has been landed on quite carefully by a pilot, and he's put some rubber on the top of it, and we can see just how many of those data points are actually going to be missing from there. So the important point to take from this is that we don't have very many measurement points defined by ICAO, but each one of those measurement points is a significant number of percent points that we can lose by dirt or obstruction or any other contaminant.
Thank you very much. Thanks, Paul. Excellent, you know, and I think this really brings it home to everybody, the importance of maintenance. And we've just mentioned about a runway, and sadly, you know, in India with the accidents in India, is that rubber deposits on the runway. And then hopefully, you know, the action was taken to remove them. But that rubber also goes onto light fixtures, eh? And that's where we tend to find that we get rubber deposits, and it goes directly on that bottom area, eh? Because then the rubber, you see it being built up. If you see a dirty inset light fixture, for example, in the touchdown zone on a category 2-3 runway. Tony, have you got a comment about coming backwards to the ISO Candela diagram and the elements associated with the other ellipses as well? Because we have the inner ellipse, where we concentrate on when we get the light fixture in the field and we're maintaining it in the workshop. But what about these others? Where did they come from? You know, what's the aspect which Paul alluded to there, saying the pilot has a wider vision. For example, it might be an angled approach and only aligning with the runway at the last moment, center line of the runway at the last moment.
Yeah, where did those ellipses come from? Best to go back into the history, and I mean, high intensity approach and runway lighting is the idea is over 50 years old, 60 years old now. And initially, when the lighting designers and users were trying to put high intensity lighting into operation, the way that they could make their lights in those days consisted of a light source put into a parabolic reflector. And what that effectively does, it produces this typical bell-shaped distribution. The center of it is the highest intensity, and then at some distance from that center, you get down to a point which is actually a third of the peak, and the average in that area, whatever that average is, then you can specify the light by saying, oh, well, the average intensity is 20,000 candelas, so there shouldn't be any light more than 30,000 candelas. That's the peak. There shouldn't be anything less than 10,000 candelas at the edge. And because of the nature of a normal distribution, if you specify those 3 points, you also specify what we call the tails of the distribution, what happens further out, down to a very low level. And that's what was being provided. When the technology developed, people started to use lenses and things to shape the beam, then it was possible to meet that inner ellipse average with quite narrow beams with very little light outside that central area. And that was degrading the system, because the reality is, on an approach, for example, you take an approach light, the initial contact, let's say in a category 1 situation, around 200 feet, with the first light in the approach system. If you think about it, that light has a setting angle, if I remember correctly, of 9 degrees. Your look down angle from the cockpit, the light you're actually looking at is another 11 degrees, 20 degrees down. So it's 11 degrees off the peak that you're looking at. In other words, these outer isocandelas are important. And you'll find that's true of all the approach and runway lighting, that a lot of the time the pilot is not looking at light within that central area. Quite a lot of the time he is, but there's to maintain the picture you've got and increase it as you continue the approach, you need those outer distributions as well. And in doing in manufacture, you demonstrate that all those isocandelas are met for the purposes of sort of first level monitoring, if you like, in the field that TMS, for example, do. Then one's making a reasonable assumption. If that inner ellipse is correct, if you've got the main intensity there, then there's a very, very high probability the rest of the beam spread, which is so vital, is also there. That's where they come from.
Thank you very much, Tony. Thank you. And it's really good, everyone, to have the historical knowledge and the understanding of why these ellipses had been and where they came from, and etc. From someone who is actually directly involved in the historical data, rather than some of us that we've learnt about it from the from the master. So thanks, Tony. Let's move on a little bit and then go onwards from the explanation from Paul, and let's just remind ourselves that about serviceability and the generic percentages that we talk about when we talk about an individual light fixture. when an individual light fixture falls to 50% and below of its design function, so if it's a 20,000 candela approach light, if that output falls and the inner ellipse to 10,000 candela and below, that light fixture is deemed to be unserviceable. And therefore, from a maintenance, an operational and a maintenance viewpoint, we want to make sure that we service those lights before that happens. And therefore, this is where the 70% criteria came in, which if a light fixture, individual light fixture falls, light output falls to 70% of its design, which we call 100%, then it's deemed to need maintenance. And then if we have two processes for maintenance, really, we have elevated lights and we have inset, in-pavement lights. And generally speaking, elevated lights are maintained in the field. But inset lights, in-pavement lights, it's a one-for-one change. So the servicing of inset lights generally is in the workshop, where they are dismantled and assessed and rectified and retested. And therefore, you know, so there is a different approach in the maintenance factor. And
Keith, can I just make a comment there?
yes, sure, yes, sure you can.
It's just for our USA and any of our listeners who work to FAA standards, there is a slight variation on this, although the result is very similar. The serviceability level under FAA advisory circular guidance is 70%. So the 70% is a threshold for a serviceable light under FAA standards, but it's calculated in a slightly different way, taking a vertical and a horizontal slice of the beam. Just for those of you out there that do that, I'm aware that there is currently a study, some work being undertaken by the FAA, and it may be, though I wouldn't expect things to happen quickly, but there may be some harmonization and they may be adopting the ICAO standard in future, but that's currently under discussion. But for those working to FAA standards, 70% is a serviceable light, but it's calculated in a slightly different way.
Oh, thanks.
Can I also add into that one as well, Keith?
Hmm?
Can I also add as well that the MARMS photometric system will measure to the FAA methodology as well as the ICAO methodology. And whilst we're on this slide actually combines information from two ICAO documents. The first one is ICAO Annex 14, the one we all know and love, which basically in black or white says above 50% a lamp is serviceable, below 50% it is unserviceable. Now, the figure 70% is actually directly mentioned in ICAO document 9137, the Airport Services Manual Part 9, where it actually says for practical reasons, replacement of a light is recommended when its output falls below 70% of that specified for a new light. So that is where we get that 70% from. So this very simple graphic pulls together the information from those two documents.
Very interesting, a very interesting comment there, Paul, because you know 100% correct in saying in the Airport Services Manual, but the Airport Services Manual was written, the last issue was 1983. So we get on to 40 years ago. So that 70% has been around a long time, eh? And it was based on constant halogen technology, lamp technology. And of course, we now moved into LED technology. But it's still very valid because whatever percentage you decide to do, then you need to do maintenance before it becomes unserviceable. So it's logical to retain that 70%, isn't it? Hmm?
And again, within the MARMS system, you can modify that 70% level on all of our reports. Our reports are coded red, green, and blue, where a blue bar for a particular lamp will be between the 50% and whatever maintenance level you've chosen. So if you wanted a maintenance level of, say, 85%, our bar charts will indicate that at whatever specification you have, and then they will draw that in blue to signify that maintenance is required.
So you can change that then, Paul?
Yes, you can't change the 50%
that's
value. That's written in stone. Below 50%, it's a failure. But the level at which you require maintenance to be done, you can alter anywhere between the 50% and 100%. And most people start off at 70% and they aim for that. Some customers of ours have actually raised that to a higher level, but I don't know of any that lower that value.
Paul, I would, Keith, I would add, finally, that there is one airport I know, one little international hub airport that has actually, in conjunction with its regulator, increased the unserviceable level to 70% and has 80% as a maintenance level, which is...
So very flexible. That's the beauty about it, is that, you know, that we have the standards and we have the generic side, but an individual airport, providing they decide to be above the standard, can do so. But of course, the bottom line is you shall not go below, right?
Indeed.
And that's a safety issue.
Exactly.
Yes. Okay. Well, let's move on. Let me move on then. Moving on to the next slide. What I've done, look, is just brought up a slide, and it's showing an inset-like diagram. There's a very principled diagram showing the CCR, the primary circuit, a transformer, the secondary circuit with the connectors into a light fixture, and the various issues which can happen, which will affect light output. And on the left-hand side, I've spoken about internal issues, just a couple of bullet points about internal issues. And then on the right-hand side, there are external issues, and they're the two factors we want to really move to. On the internal issues, tungsten halogen. Tungsten halogen didn't care whether it got AC or DC to it. You know, it's a filament in a gas. But when it comes to LED, it's brought us a lot of different issues. And we don't have time in this webinar to talk about the LED and all the different issues that the LED has brought us, but we'll talk about one element of it. On the external side, then of course, you know, getting dirty, getting rubber, etc. So this is a nice little diagram which just puts quite a few factors into the equation of why we have low photometric output, the reasons behind it. And one of the things I want to bring up now is what's happening associated with LEDs, particularly. And what I'm going to say is thank you very much to Cooper Crouse Hines in the US and the Canadian Airport Electrical Association. And because this is an extract from a presentation last year, and what was considered is, why do some of our lights get condensation inside when they are sealed units? Well, actually, Cooper Crouse Hines did some investigations in detailed analysis, and very interestingly, although it was done on an elevated light, maybe the same principle will exist for inset lights, but what happened is there is differential pressure between the atmosphere on the outside of a dome, a globe, and on the inside because of temperature. For example, if we've got an elevated runway edge light on one side of the runway, and we know they're at nominally 60 meter spacings, then one side may have the sun on it, but the other side may be in the shade. So that in itself, those temperature changes also affect internal pressure. And then therefore you get external atmospheric pressure and internal pressure. So there's a differential. And what's happening is that all our light fixtures, whether it's an inset light or whether it's an elevator light, are sealed using some form of gasket. And those gaskets themselves have their criteria of performance. And therefore, if there are changes between temperature changes externally and internally, and with LEDs, the internal temperature is going to be dramatically lower than a tungsten halogen, which we already are aware of, then there's going to be some differences. And in that differences, then if anyone, those of you out there know about taking an inset light, for example, and you take an inset light which has a lead, this secondary lead, and we have to plug it into the, put the inset light into a can, into a base unit, and we have to connect the lead to the secondary cabling, which goes out to the, transformer. And if you've got a pinprick, just a pinprick in that secondary cable, then because of this differential, then it will suck the water in. And so you will find you have water inside your fixture. Now, it has been found by this investigation by Cooper Crown Science that can happen purely because of changes in atmospheric temperature between one side of a light fixture and the other side of a light fixture, say in a dome, and then ultimately there's a failure of the gasket. It goes outside the parameters of the gasket, and it's really been an interesting study, and it's really highlighted some of the issues associated with the migration from tungsten halogen to LEDs, which we previously really was not aware of, that this factor could affect actually light output. So if you've got condensation inside your lens, on the inside of your lens, there is no real difference to having rubber on the outside. It's deteriorating the light output. And so moving on to the likely scenario that has really come up with this is that during the day, the sunlight heats the fixture, increasing the internal pressure, and then that will slowly lead to equalize with the external. Then at night, the fixture cools and certainly when, for example, if we take the Middle East regions, those of us who think that the desert is hot want to work in the desert at night, with high temperatures in the day, but you are absolutely freezing at night. Okay? There's dramatic changes. So those kind of scenarios, those kind of locations are pretty prone to this kind of situation. Then also there's the humidity side. In sunlight, and is it dry air? Is it wet air? That kind of scenario. Is it spring and autumn, summer and winter? Those elements occur. And of course, if you've got condensation, then it becomes water. Ultimately it becomes water, and electronics inside an LED light fixture creates corrosion. Even if you encapsulate everything as near as practicable, then corrosion will set up, start to occur. And if it's left, then ultimately, then we will get, in fact, we'll get a growth inside our light fixture, etc. So LEDs have brought different demands on us. That's what I'm trying to bring to the attention. So this is one factor, just one small factor about internal issues associated with a light fixture. And I've got one more slide to show on this one. It's taken to say thank you to the Canadian Airports Electrical Association and Cross Hines I've shared this, and I think this right-hand side one here is nice. You get the higher pressure, you get the lower pressure, and that's what happens inside, right? And really, it's something that we need to take into consideration of as we look at LEDs and the future. So moving onwards to external issues, then rubber. And I've showed two diagrams which Paul has provided, and there's a runway a touchdown zone and a runway centre line.
Sorry, no, Keith, just to correct you there, they are both runway centre line.
Okay, thank you.
But the top one's 7-degree elevation, so it's 30-metre spacing.
Oh,
the bottom
30,
one
sorry.
is a 15-metre spacing. But they are essentially, they're both straight fittings with slightly different shaped ellipse, just because they're different. But the colours in the picture are there to kind of indicate what we're talking about here.
Yes, okay. So clearly, if we would expect the highest intensity to be right in the centre of the beam, hopefully.
Yeah.
Of course, if there's towing, that's depending on, it will be showing it left or right accordingly. And the bottom one there is showing that, oh my crikey, we've lost the light output, it's showing red. Hmm?
Yeah.
So, and principally, that's how it would be shown in an ISO Candela report for a dirty lens, and typically with rubber deposit. Eh?
Yeah. We show a false color image, if you like, to try and indicate where the brighter parts of the beam are. So the kind of more bluey white areas of our ISO Candela diagram show a bright spot on the beam, and the darker colors, the reds, show us where there's low light output. So by just instantly looking at those two diagrams, I can see that the top one has got a very bright output, straight ahead, slightly high of the ellipse, but nevertheless is compliant. And the one below is very, very dim. And when I think of the picture at the bottom, I think of something like the lens that we can see there on the left of the picture. As you can see, of those measurement points, a significant number of them would be obscured by the rubber that is on that fitting. So the simple way to resolve that issue is to clean that fitting.
Correct.
Just make a comment there. That bottom picture is very interesting, because if you notice, the worst condition is at the top of the diagram. That's where there's the least amount of light. The rubber, most of the rubber is at the bottom of the lens, and that's a natural situation. If you use a lens system, the image is inverted. So, if you think, well, it's just at the bottom of the lens, that's going to be at shallow angles and doesn't matter very much. It's not true. It's just the reverse. The very, very contaminated bottom half of the lens will produce very, very large reductions in the amount of light at the higher angles.
So we're actually saying it's the focal point. As we go through the focal point, it changes over, right?
Yes.
Yes. Oh, so we're into camera technology as well, eh? Yes, that's very good. So here I've shown another picture here, which is very similar, but of course one's showing it so that where the highest intensity is, which is right in the center, so it's a straight lens, eh? And whereby if you have if you took that same picture on a light fixture that has its built-in towing, then it would be shown off either to the left or to the right. That is correct, is it, Paul?
Well, yes and no. The two particular images there are both for a straight fitting, which shows that the bottom image is looking at a fixture that is supposed to be pointing straight, but in actual fact is towed off to the left and too high. If we did have a towed fitting, then that ellipse, the center line of that ellipse would be shown at whatever that tow angle is. So, for example, it would be, yeah, along the bottom there, it would be, for example, -3 degrees for a towed left 3-degree fitting.
Okay, and I think this is important for us just to have this briefing associated with, asking such questions as this, because naturally, if we are going to do photometrics in airports, and our maintenance team need to have that appreciation.
A lot of the interpretation of these comes from experience of the engineers themselves who use the photometric system. They look at the diagrams, they go and see the fitting, and they kind of work out for themselves very quickly when they see this kind of picture what is wrong with the fitting. And as an example, if that bottom fixture was a halogen inset center line, my guess is that the halogen lamp either has a broken reflector or isn't seated properly, which is why it's shining off quite brightly, but to the wrong angle.
Okay, thank you.
And I would deduce that without even taking the fitting apart. I could be wrong, but 9 times out of 10, that would be the first thing I would look for.
Thank you. I'm looking at the time, and so I want to move on, and I want to say, well, how do we do these cleaning, eh? Because we do want to show a couple of case studies, and what we do about dirt, because that's dirt on our lenses, whether it's glazed lens on a runway edge light because of the jet blast, or whether it's the touchdown zone with rubber burning onto the lens, then we have to clean it. There's been a whole range of traditional methods of walnut shells, using dry ice. Dry ice was thermal shock, so that created its own problems, even down to using a brush with detergent. The issues, though, with the detergent, it has a high pH factor, and it was found on one study that if you use a detergent with a high pH factor, it actually attacks the aluminium alloy of the fixture itself. So over time, it can actually fracture. So there's an issue to consider. And so what as the investigations and ultimately then is, if we had a tool which would actually be carbon neutral in today's day and age, eh? And so a bicarbonate of soda material, which is probably negative in terms of its pH and factor, more alkaline more than acidic. And but if for example, I had to do a runway center line on an active airfield, and I had something like 200 light fixtures, it's pretty time consuming. So to have a tool which can be used easily and quickly would be ideal. So I'm going to bring in now, and maybe whether it's you, Paul, or Robert, is to talk about the cleaning system that is available from TMS.
Yeah, well, I'll just quickly run through, as I say, we're running short of time, but I mean, essentially, rubber contamination of any sort, dirt, rubber, de-icing fluid, even sand sitting in front of the lens. All of these contaminants will prevent the photometric light output and render the lighting unserviceable. And contamination is the #1 reason for lights being unserviceable. So before you look for any other reason for the lights not performing, remove any contamination. And the most effective means of doing this is using a tiny bit of soda, bicarbonate of soda, and air in a mixture. We discovered this from a cleaning solution that's used to remove paint and graffiti from historic buildings, often made of very soft stone. People unfortunately spray things onto these buildings, stone or wood, and they discovered that bicarbonate of soda sprayed onto that in a high pressure with air in small quantities can remove paint and other contaminants without damaging the structure of these often very historic and very valuable artifacts. So we applied that. We discovered that we could apply the same technology to cleaning runway lights, and it's proved highly effective. Because not only does it do the job extremely well, removing every form of contaminant that we've come across, but it also does it very rapidly. It uses a biodegradable compound, bicarbonate of soda, which doesn't leave any residue. It's used in such small quantities, and is cheap and ultimately very effective. It takes considerably less than 10 seconds per bidirectional fixture, so you can clean each side of the fixture with less than 10 seconds. And indeed, if they're not contaminated, it can be done even quicker than that. It can be applied either using an automatic machine or as an operator with a lance. It's environmentally friendly, as I've already said. It doesn't damage the runway light, doesn't use any chemicals or water to contaminate the fixture, get inside the fixture, or leave any residue on the runway, which could which could potentially in colder climates turn to ice. There's no thermal shock to the fixture, as you would get potentially with dry ice, which can crack the lens, as it's an ambient temperature cleaning medium. It's integrated with our other tools which allows you to, if you performed a MARMS test, you can use that data to direct the cleaning system to only those fixtures which are 70% and below, meaning that you can maintain the runway in the absolute minimum of time.
Okay.
If you
Thanks,
turn the, yeah, thank you.
So I'll move on then to your case study, Robert.
Right. Well, we just want to run through a couple of examples here. This is one where I went to an airport to perform a demonstration. This airport is a major international hub airport, we did a demonstration. And when I arrived at the runway, they had many runways there. I asked the supervisor. I said, "Well, how?" I could see immediately. I said, "Are they 100%?" And he said, "Yes, they're 100%." I said, "Well, how old are these lights?" He said, "Well, they're 2 years old." And they didn't have any photometric test equipment. They only replace on failure. And I said, "Well, how often do you clean your lights?" He said, "Well, we never clean the lights. Only when a light fails is it replaced in the runway, following a visual inspection, and then of course it's cleaned in the workshop." We tested the runway. This is the result we got. 8% of the lights were serviceable. So it's absolutely shocking, really. The performance of these lights was, in low visibility conditions, they would not be visible. So that demonstrated the need for cleaning. So moving on to the next slide, you can see an example where the lights are cleaned, and we've seen this on several airports, where the lights are cleaned by hand. Very arduous, time-consuming, and extremely painful, particularly if they're often performed by the electricians, the people that do all the work on the lights. But some like myself are not the youngest people in the world, and it's extremely arduous and painful to be on your knees scrubbing lights, and particularly if they have contaminants on them, such as rubber, which is very difficult. You have to use some kind of chemical with a rag and cloth and scrub, and the results on the left are, this is a very good airport, and they achieve serviceable results, but the results on the left is what they would achieve typically following a manual clean with a photometric test. On the right, they use the MARMS photometric, the MARMS cleaning machine, and they achieved these results, which is a considerable improvement. In fact, they reported their best ever results following that. And this is an airport that never closes. So when you're working on a live runway, not only are you getting much better photometric results, because if you can improve your results to the level on the right-hand side, that means they're going to become unserviceable in a longer period than the results on the left-hand side, which take longer to do and require longer to do physically and require more runway access than the soda cleaning results on the right-hand side. And then finally, this example here, this is an example from a touchdown zone which we've tested recently, and these are all the tests on the runway completed on the year to date. And as you can see, this runway is cleaned regularly, but in spite of that, the results are never above 70% by and large. As you can see, the red results reflect unserviceable results. The blue is between 50 and 70%, and only the green are above 70% maintenance level. And only with the soda clean on the left-hand side did this runway achieve the serviceability that's actually required for Cat 3 operations. However, even with cleaning, you can see 3 of the results were actually below 70%, even though they were close. So what was the reason for that? Well, on closer inspection, you can actually see that rather than just being LED lights, I've heard it described as maintenance free. Even the lenses get scratched, and these lenses are over 5 years old now. And if they've been out there for that amount of time, they do get scratched, and the lenses have to be replaced. And so from cleaning the lights properly, you can now target those with the poorest performance still for lens replacement, and that way they will become above the maintenance level, and maintenance intervals can be reduced. And obviously, the less maintenance, the more you have to do, the more runway availability you have.
So what you're saying then, Robert, and what you're saying here then is, if I could interact here. So, I think we're demonstrating very clearly, that a cleaning regime is pretty mandatory as part of the serviceability element, the compliance of AGL. But a cleaning regime which is managed and using the correct tools make it fast and easy. And also we can give results which can be demonstrated and fed into an asset management system like the MARMS engineer stroke dashboard concept, so that it can be very, very quickly and in real time presented that for example, if this were this kind of thing was available in all aviation investigations where there's incidents or accidents associated where AGL is, where the finger is pointed at AGL, this would be absolutely superb, wouldn't it?
It would. It demonstrates the airport is indeed operating safely. Correct. And we understand it's not easy, but you need the tools to do the job, and then ultimately you need to do the work.
Okay. One of the most effective ways of improving your light output, this quite clearly shows, is to simply clean the fitting. No taking the fitting out, no taking it back to the workshop, refurbishing it, whatever. Start off with a simple clean, get a good cleaning regime into place, and you can maintain your serviceability level very, very easily.
There's also the time then, Paul, isn't there?
Oh yes, it's very quick operation.
So it's very, very quick operation to do it, using the correct tool for cleaning, as we've demonstrated, and it's environmentally friendly, etc. But the other aspect is if you still adopt the traditional maintenance of taking an inset light fixture out and replacing it with a serviceable one, that in itself brings additional demands. Because it's time consuming, and also, you've got to do other mechanical functions associated with it and electrical functions.
Yes, indeed. And as once again, Keith, we're having so much fun. We're running over time, but
yes,
I think we better look at some of the questions we've got coming in, but one is pertinent to this point here. And it says, if we clean our AGL before photometric testing, is this cheating? Which is an interesting question I've had before, because of course there are airports that will test minimally but conduct a thorough clean before and maintenance before the test to produce photometric test results to demonstrate compliance. Well, of course, this whilst this and will enable an airport to potentially produce very good photometric results, the whole point of this is not to impress a regulator. It's in fact to provide safe operation. And I know that in certain regulators, and I can speak for the UK CAA, the inspectors will look at the test results over a period to see that these are being consistently achieved. So in fact, you know, if you can at all do this, what you should do is do the photometric test and then the cleaning afterwards, based on the results, because what you had before is what the pilots are getting as a lighting service.
There's also another thing, Robert, there, which is that by having that process, you do the photometric and then you do the cleaning. If you do the photometric first, it then starts to give you the records to determine the periodicity at which you should do the photometric test, which
Yes.
then identifies the maintenance that is needed.
And another thing, even though cleaning is a particularly efficient way of restoring the lights, once they are clean, if you've got photometric data which shows you which ones are the ones which need the recurring maintenance, i.e. the ones that are shown in blue, then you go and you target clean. You don't clean the whole runway every time you go out and do a clean. So again, you're saving more time and effort.
One of the other aspects, of course, which is the other side, although we're dealing in photometrics at this moment of discussing photometrics, is the other factors which can affect photometric output, because pavement deteriorates over time. And on a touchdown zone, then you have you have 900 meters of touchdown zone. Then the first 300 meters from the threshold, generally speaking, is probably lower risk area. The middle 300 meters of the high risk area of a touchdown zone, and the final 300 meters up to 900 meters is a medium risk area. And the center, the high risk area, then that's where the PCN element of the pavement itself gets hammered because of the aircraft coming down. So to do these kind of tests with photometrics will also identify if there's an ongoing issue on the other factors, and specifically, say on the civil side, it's aiding the civil engineers.
We have seen occurrences where customers of ours have said, oh yes, lamp XYZ, that one always fails. We know that because when we go to have a look at it, it's tilted, it's moved. What we've got to do is some civils work before we can do anything else. So they know their airfield, they get to learn their airfield and where these problems are by looking at regular photometric inspections. So it is recommended that you do them on a regular basis and not just do the maintenance once a year, as Robert said earlier.
Right. Moving on, as I said, with questions. Tony, Mohammed would has commented, do we know why ICAO does not revise document 9137 that we discovered earlier, 9137 part 9? It is too old, he says. Do you think this needs revision, Tony?
Yes, I think this is a topic we've aired a little bit in previous webinars, and certainly the ones I did on PAPI, for me, highlighted it. The most of what we've got, I know there have been amendments over the years, but much of what we've got in Annex 14, Aerodrome Design Manual Part 4 and so on, have their origins at least 40 years old, and some of the electrical stuff until quite recently was 50 years old. And ICAO really to be providing a proper service and keeping operation safe and regular, all of its manuals need a very strong revision in the light of operational conditions today and change in technology. We've been talking about LED. We've heard in the last 10 years all the benefits which are focused on lamp life being incredibly long.
Right.
What we were hearing today, the hint that maybe because there isn't enough heat in there, the condensation is more of a problem than perhaps is even recognised at the moment with those sorts of things. So, yeah, I mean, the visual aids panel really could be very active and have a lot to do over the next 5 years if only there was the will to do it. But it needs to be done because now the regulations in some ways are making things more difficult.
Yeah.
To provide that service.
One of the elements associated with such as the visual aids panel and such as the technical committee in the IEC for airfield ground lighting is that inputs to that, generally speaking, can only be inputted through the national executives. That is the National CAA for ICAO or the Standards Institute in our different countries into the IEC. And that is where there tends to be a blockage in the information gathering and the information transfer because of the process of accessing or inputting information from the people on the ground.
Mm-hmm. Thank you, Keith. Yes, that's a good point. Alan Cordina says hello and would like to know if there's any provision in ICAO or FAA on a mandatory requirement of grounding rod for PAPI. I'm not aware of any mandatory requirement. Are you, gentlemen?
I think when it comes to grounding, I think he's talking about ultimately is really talking about if in the event of an external electrical influence, for example, a lightning strike or an indirect lightning strike. A direct lightning strike, there'll be nothing left, right? But when there's an indirect lightning strike, then the lightning has been shown to hit the pavement first in an open airfield and dissipate across the surface of the pavement and then go into the soft. And of course, our PAPIs, as he asked about the PAPI, is in the area in the soft, you know, adjacent to the runway, and therefore the element of grounding is associated with the electrical grounding and the counterpoise, and the counterpoise, and whether or not you should actually have an earth bar, an earth lead from the elevated structure of a PAPI to a counterpoise to dissipate any external electrical influences should it occur. Maybe I think that is the question that's being asked.
Right, yes, I would say so. But is there there's nothing mandatory about that, is there? I don't believe.
Well, unfortunately, there's two schools of thought. If you look at the FAA requirements and you look at the ICAO requirements, then it comes back to the type of feeder cable that we use, the primary cable. In the US, generally speaking, it's on-screen cable, whereby in the ICAO world, it's screen cable. So screen cable ICAO, FAA, on-screen cable. In the on-screen cable world, the FAA put great emphasis on the counterpoise. In the ICAO world, then we tend not to put much emphasis on the counterpoise, other than in those areas that are affected by high electrical activity. So there are two really schools of thought on it.
Right. Sekar has asked if we could describe the mean time between failure calculation, how to calculate fitting reliability. Are there any particular ranges to follow as per Annex 14 and FAA? Paul?
I would say there's no directives at all.
No, I would say there's no directives, and mean time before failure is quite a difficult one unless you can trace your assets. We do have the ability to trace assets within the MARM's suite of programs, but it involves tagging your fittings, tagging your runway, and then you can actually locate exactly how long a fitting has been in the workshop, how long it's been in the runway, whereabout it's been in the runway, and then that gives you the information to make your own mean time before failure calculations. But there are all, as Keith alluded to earlier on, there are all sorts of issues which affect that mean time before failure. You might find that in the heavy traffic areas, such as the middle of the touchdown zone, where there's a lot of impact, that your fittings fail earlier than if they were in the lower risk area, as Keith said, towards the threshold. So for the same type of fitting in a TDZ, there would be a different mean time before failure for an area where the aircraft landed more than where they landed less. But without actually tracing through all your fittings, where they are, or how long they've been in the runway, I think it would be difficult to come up with an accurate MTBF.
I have seen, Paul, that at airports that adopt that process of doing the one-for-one change, and maintain the light fixture, knowing, and also something which is important, then whilst we know the location using the technologies of, say, today, so we know the location where a light fixture, but also to be able to ID the light fixture itself. And when you look at those two elements, then if you look at the high risk, the low risk, the medium and the high risk areas of a touchdown zone, as an example, if you take a fixture out of the high risk area, the next cycle you could put it in the low risk area.
Yeah,
We could extend the life X of the fitting.
And indeed, that is a requirement. I know that certainly was the case under UK CAA. I don't know if that translated into EASA requirements to actually manage the location of fittings to avoid exposure to intense pressures, for example, in a touchdown zone. So asset management is the solution to that, and the only practical means is by tagging your lights. And so if Sekar, we can talk to you about that separately. Sekar also wants to know, can we describe the difference between the field photometric and workbench photometric ranges as per regulation? Let me just say that the field photometric ranges are set per the standards in ICAO and FAA in terms of the 70% and the 50%. Clearly, the level you're able to achieve in terms of light output, you'll be able to maintain them to, the higher you're able to achieve, the less intervention you're going to require on the runway. But when it comes to the photometric workbench, clearly that means that you want to achieve the highest standard possible in the workbench, and that will of course depend on the age and condition of the lights. Older lights, it will be more difficult to maintain them to as high a standard as a brand new fitting, for example. But we would typically recommend at least a 90% output for a pass rate in a workbench for a refurbished fitting. Obviously 100% for a new, 100% or more for a new fitting, but for a fitting that's been in service for a while, at least 90%. So moving on to the next question. We've got Ahsoka would like to know which advisory circular we refer to for the average beam intensity of 70% minimum. And just to show off, I'll say that's 150-5340-26C, and we'll put that in the answers to the seminar onto the website. Then Sekar asks, how to avoid the natural degradation from the field photometric? Are there any procedures to follow? That's a Paul.
Well, I guess you know, there will be a natural degradation. as we've alluded to again in the presentation, there's lots of different factors, and Keith had a slide there which showed internal factors and external factors, and basically you've got to try and work out for yourselves within your particular environment which are the easy gains. Obviously, the easiest gain for everybody throughout the world is to keep them clean. If you've got good photometric data, then you need to be able to try and keep them aligned, and then you can start looking at the other electrical issues that may surround your fittings. But you've kind of got to try and treat the whole thing as a holistic system. Every single part of that system has potential to lose you 1 to 5% of the light output. So if the lens is dirty, there's 3 or 4% gone. If it's scratched, there's another 3 or 4% gone. If it's misaligned, 5% gone. If you've got bad contacts, 5% gone, etc., etc., etc. So you've got to kind of look at the whole system and then go through in a methodical way to try and address each of those issues.
Thank you, Paul. I've got a question here from Sudhir, who would like to know: water entry due to condensation inside LED inset fittings is harming electronic components. What are the countermeasures or remedies for that?
Very interesting. When we looked at the the Kraus-Heinz study, and they've obviously done a lot deeper than we could possibly talk about on a webinar. And there was also the introduction of different kinds of gaskets, and we can provide that kind of information, separately. And but the information that we have on those environmental gaskets, then I can't speak for all the light manufacturers.
I don't know where in the world Sudhir is from, but again, with inset fittings, LED or halogen, they tend to be in a can, and that can fairly often is part of it. It acts as part of the drainage system of the airfield, so all the conduits that all the cables are in will leak water in and hopefully out. But if you've got water sitting in the bases, then you've got a drainage issue. And if water is sitting in the bases, as they warm up and cool down, they will suck water in. And unfortunately, water goes to the bottom part of the fitting, which is where the manufacturers, for some bizarre reason, seem to put all of their electronics.
Vasilis makes a point here, which I'd like you to address, Tony. He says the taxiway and approach lighting needs photometric test. Discuss.
Does approach lighting need photometric tests?
And taxiway lighting.
Or taxiway lighting? Taxiway, yes. My view is that increasingly an aircraft operation is what in piloting terms is called chock to chock. In other words, your task for the day starts, as far as the aircraft's concerned, with the pushback as you depart on the apron, the taxi out, the line-up takeoff, flight to destination, the approach, the landing, the ground roll, the taxi in, the docking, until the engines are stopped. And the more seamless that is in every way, that's the way the world's going, I think. For a long time, responsibilities were so segmented. There was a whole lot of approach controllers who did approach control, but when the aircraft was within sight of the runway, effectively, they lost interest, and then somebody else took it over for the landing, and then somebody else for the ground movement. Very much you might call mandrolic, but today so much is done with avionics, and with GPS becoming more and more important in every phase. We now have a requirement really for the ground movement side of it to be integrated and have the same levels of performance, reliability, and so on as what's in the air. and it's just as important for both safety and regularity. I think when you come to the matter of ground movement, two things. One is the increasing use of switched centre lines, follow the greens. Keith's addressed this in early webinars. There are some dangers and pitfalls in there in the way it's actually engineered. I don't think it's necessarily totally robust at the moment, although I ran a program in the EU over 20 years ago called DFAM, where we demonstrated the principles of this at Cologne-Bonn with an aircraft taxi around following the greens, with data from sensors as to where the airplane was and so on. That's the way it's going. But the one thing I think many people in the maintenance world will think is, well, the thing is, if you're telling me I need to have high levels of maintenance for approach and runway lighting, but of course that's different from on the ground, because if you're at 100 feet and all the lights go out, that's rather dangerous. You can't stop. Whereas if all the lights go out on the taxiway, you simply stop taxiing until it's fixed. I think that's a very naive way of thinking of it today. I think you've got to think of it's just as important, for various reasons, a mixture of safety and regularity, that the taxiways are as reliable and meeting the specs as much as any other part of the AGL.
Right. Well, thank you very much, Tony. Look, we once again we've considerably exceeded our allotted time. Keith, if you could just step forward a couple of slides on your presentation there, because I just want to make one final comment.
No, that is the final slide.
Oh, right. So
Yes.
if I get in,
I'll stop sharing.
Okay then, and I will just share my one slide here to say what's coming next. We have this presentation here next week. Steve Hutton has very kindly, with the agreement of Oman, Muscat International Airport, agreed to do a case study from an airport that covers how they maintain their airport. And they've won a number of awards for excellence. And Steve is putting together a presentation to describe exactly how they operate and how they go through the process, which I think we'll all find very, very interesting.
Well, I think this is very, very important, Robert, you know, because, you know, Muscat International, as you say, it's a very, very busy airport. It has a lot of international flights, and it's in a region of the world which it's close to the sea, okay? And it's in a region of the world where they have the temperature changes and high temperatures, the introduction of LED technology. So it's going to be a real interesting week next week, and Muscat have done exceedingly well.
Yeah. So I'd like to thank Keith, of course, and Tony and Paul for their contributions to the presentation, to the Q&A session. And of course, I'd like to thank you all for joining us today, participating in our webinar, and all your very, very good questions. We'll be posting answers on the website in the next 24 hours. So if we haven't answered your question, or you want to check exactly what we will reiterate what we've just said and think about it a bit more. It will all be available for you on the website. So thank you very much. We'll have a copy of the presentation as well, and we'll see you all next week, hopefully. Thank you very much, and stay safe. Goodbye.
Bye.